Is the video for NIECE Chapter 5. So before I actually begin talking about the content of our first chapter for this course, I just want to say a couple of introductory things. First of all, I'm recording these YouTube videos for the chapters that I teach in Geography 2130 Meteorology, primarily for those students who are taking the course as a distance course. So when I go through this PowerPoint, and particularly at the end when I give the assignment for the lab and the KHP section of our class, this is going to be the assignment for the students who are taking this class as a distance class. I understand and I fully expect that there will be students who are taking my class in the classroom face-to-face who will look at these videos, particularly students who miss classes because they have some sort of an activity or have been sick and they need to view this video to make up the material. So understand that the PowerPoints that I'm actually covering here are pretty much identical to the PowerPoints that I teach in the classroom during fall semesters. So if you are a face-to-face student and you're watching this video or any of the videos to follow, know that I am covering everything that I cover in the classroom. Just know that at the very end, when I give the assignment for this particular chapter, that the assignment is for the distance sections of this class, and it does vary from the assignments that I give for the face-to-face section. So having said that and understanding the differences between the face-to-face and distance sections, let's get started with our first video of the class. And the topic for Chapter 5 is satellite and radar. And this is actually a really nice topic to begin with because everybody in the class has some sense of satellite and radar. And the vast majority of the students who are taking our class are aviation students, and so you guys are in particular pretty well aware of how satellite and radar work, but I'm going to go into probably a bit more detail than what you already know. So I'm going to do a slideshow, and there'll be a slideshow for every single one of these PowerPoints, and the PowerPoints are animated, so things will appear and disappear on the slides, mostly appear. But let's just get started. And so we'll begin this PowerPoint and the slideshow from the beginning. So we're going to begin with Doppler radar, and this is just an image of a Doppler radar and what it looks like. So what we have here is the radar actually on top of a platform, and the radar is actually located inside of this shelter that looks a bit like a volleyball. So the radar is inside, and it actually rotates around relatively quickly so it can sense the atmosphere on a pretty frequent basis. And so we refer to radar as being a remote active sensor. So what a remote sensor is, it is a sensor where the instrument is remote to the phenomenon that it is measuring. So when we're talking about Doppler radar, we're talking about Doppler radar measuring either the precipitation in a cloud, so it's measuring cloud particles, liquid droplets, ice crystals, or it's measuring motion to or from the radar when we're looking at Doppler radar in velocity mode. But the clouds and the atmosphere that are being measured by the radar are remote to the radar, which is actually located just above the Earth's surface. We also refer to Doppler radar as an active sensor because the Doppler radar is actively sending out pulses of microwave energy that are then being scattered back to the radar by the cloud particles, by the droplets and the ice crystals. And so the radar is actively sending out a signal which is then being scattered back to it. On the other hand, we're going to also be focusing on orbiting satellites. And so these are the satellites that we use to measure or to observe the state of the atmosphere well above the Earth's surface. And we're going to take a look at two types of of orbiters in our class. In particular, we're going to take a look at geostationary satellites, and these are the satellites that are indicated by the green dashed line. So satellites are remote passive, and I'll say more about that in a second. But GOES, or geostationary orbiting environmental satellites, these are satellites that are fixed above the Earth's surface, above the equator, and they basically move around the Earth as the Earth is rotating about its axis. And so from above, it looks like the satellites are actually moving, but from the Earth's surface, what we see is that the satellites are actually fixed above a point at the equator. And we'll talk a little bit more about that in a moment, but you can see that GOES West is basically fixed at the equator at 135 degrees west, then GOES East is focused above the equator or fixed above the equator at 75 degrees west, and they orbit around the Earth at about 22,500 miles above the Earth's surface. On the other hand, polar orbiters do not stay fixed above a point above the equator. Instead, what polar orbiters do is they basically orbit from pole to pole going around the Earth, and the Earth basically is rotating beneath the polar orbiters as the polar orbiter remains fixed in the same location as it orbits. So unlike the geostationary satellites, which are actually moving around and basically tracking the rotation of the Earth, the polar orbiters, if you take a look at them remotely from outer space, they remain at the same location and the Earth rotates beneath them. The polar orbiters maintain a much lower orbit above the Earth's surface, only about 530 miles above the Earth. Okay, so let me actually, before I move on, let me say something about the type of sensors that satellites are. These are, again, remote sensors because the satellites are located well above the Earth's atmosphere, and basically what they're doing is they are basically sensing the Earth's surface and the atmosphere from a location well above the Earth. So the phenomena that they are sensing are remote to where the satellites are located. In this case, we refer to satellites as passive sensors because the satellites are simply passively measuring the energy that the Earth is sending out to space. And as we'll talk about soon when we talk about the difference between visible and infrared and vapor satellite imagery, it is the type of energy that is being sensed by the satellite sensors differs, but in all cases, it's simply passively sensing energy that the Earth's surface and atmosphere are sending out to space. Unlike radar, where the radar is actually actively sending out a signal that is then being scattered back, in the case of satellite, the sensors that are located on the satellite aren't actually doing anything other than measuring the energy that it's receiving. So they are passive sensors. Okay, let's move on and let's focus a little bit more on geostationary satellites. So this is a full disk image of the Earth from a geostationary orbiting environmental satellite, and this is from GOES East. In other words, this is the satellite that is fixed above the equator at 75 degrees west. And so it's not just taking an image of the United States and Canada. In fact, it's taking an image of the entire disk of the Earth beneath it. And this is obviously during the middle of the day so that the entire disk is illuminated by the sun during this particular moment. So this is an east full disk satellite image. And again, the satellite is fixed roughly above 75 degrees west, always at the equator. And again, as the Earth is rotating about its axis, the satellite is moving with the Earth so that it stays fixed above this point at all times. Here's an image, again, full disk daylight from GOES West. And again, GOES West is located roughly about 135 degrees west. Actually, it's about 137.2 degrees west. Again, full disk. This one is all daylight, so the entire disk is illuminated. Now, unlike geostationary satellites, which are fixed over the equator, we actually have polar orbiters, and the reason we look at polar orbiting is because if we go back just a slide this to our geostationary disk, what you see is that the geostationary images do a really good job of sensing the Earth from the equator up to about 50 or 60 degrees latitude, both north and south. But what you see is we really don't get much information at the high latitudes. So we begin to really lose our image up here. It's much more flattened out near the north and the south poles, and we don't really get a good image from above. And again, if we take a look at east, you see the same thing, that we really begin to lose the high latitudes of the northern and the southern hemispheres. And so we take a look at polar orbiters because what the polar orbiters do by basically circling from pole to pole several times a day is they actually allow us to see with much better idea of what's going on at these high latitudes. So here is a polar orbiter image of Alaska and Western Canada. Now, one of the great benefits of polar orbiters is that we can really see what's going on at high latitudes. One of the drawbacks of polar orbiters is that they don't actually sense the entire disk at one time because they're in a really low orbit. So what you're seeing here for this particular pass of a polar orbiter is basically the slice of the Earth beneath it, where it's actually able to pretty well sense what is going on. So if we actually want to get an idea of what's going on over a larger geographic region, and I don't actually have an image here, what you have to do is actually kind of stitch the images together, and they're offset by a little bit of time, so it looks like a bit of a Frankenstein image if you actually want to take a look at what's going on over a much larger geographic region. beyond what the polar orbiter is sensing during a particular specific pass. So just to give you an idea of what some of our images look like, here's a visible satellite image, and we'll talk more about visible satellite imagery in a moment. Here's what the same image looks like on infrared. In better words, what's being sensed by an infrared sensor on a GOES satellite. Here's what negative infrared looks like. I don't know why the text shows this, by the way. We never look at negative infrared imagery. So this is the only time you're going to see a negative of an infrared image. And then here is a water vapor image. We're going to spend a bit of time talking about visible, infrared, and vapor imagery. And again, we will never speak of negative infrared imagery again. So this is what we're going to focus on. Now, what I want to make clear as I move on, just to be really clear here, satellites don't actually take these images. Satellites don't collect information. There are sensors that are attached to the satellites, and it is the sensors that actually sense the energy that's being received from the Earth's surface and the atmosphere, and then the sensors relay this information back down to us down here on the Earth, and we make these images. The satellites are just the vehicles that carry the sensors. All right, let's talk about visible satellite imagery first. So visible satellite imagery is basically made up, and basically what it's doing is it's showing us a visible picture of the Earth and the atmosphere. What the sensor is actually measuring is the visible energy that is entering the Earth's atmosphere from the sun. It's incoming visible energy from the sun. And then what the sensor is measuring is the energy, the visible energy that is being reflected back to it by the Earth and the atmosphere. We refer to this reflectivity as albedo. So every object has an albedo. And what the albedo is it's basically telling us the fraction of visible energy that is reflected by the surface back outward again. So if the albedo of an object is 0, basically what that means is that it has 0 reflectivity. In better words, it is absorbing all of the energy. If the albedo is 1.0, that means that the object is a perfect reflector, and what we'll see reflected outward is the color white. In better words, all wavelengths of visible light are reflected perfectly by the object. Albedo only refers to the reflectivity of visible energy. So albedo only refers to visible energy. It does not refer to infrared, microwave, ultraviolet, or any other type of energy that we will be discussing in our class. So just make sure that you understand that when we're discussing albedo, we're always discussing the reflectivity of a surface when it comes to visible energy, visible light. So if we take a look at this image, this is an image of the eastern half of Pennsylvania on a day where there's snow cover and also some cloud cover. And so what we're looking at now is the albedo of the Earth's surface and the clouds. And just for reference, you can see basically a topographic map of eastern Pennsylvania and some adjacent areas of Delaware, Maryland, New Jersey, and New York as well. But this is really focused on eastern Pennsylvania. I will mention that our authors are basically from Penn State. I actually went to school with our authors many years ago, and so they're still professors at Penn State. I believe Grency is retired now, but Nice is still actively working at Penn State. And so I know these guys, and because they're at Penn State, you're going to see that some of our examples are going to be a little Pennsylvania-centric in our class, but that's okay. It makes the point. Now, going back to the visible satellite image, what you're going to notice is that there's a lot of white here, and this white refers to snow cover. So here's Philadelphia, southeast corner of the state, and what you'll note is that there's no snow cover just in the southeast corner around Philly, and then as you begin to move north and west of Philadelphia, you'll begin to pick up snow cover, and snow, as you know, it's bright, it's white, it has a high albedo, and so the visible satellite sensor is picking up this high albedo, and we are color coding this data white. Now, where we have a lot of forested area up here in the Pocono Mountains, you'll notice that we lose the white. That doesn't mean that there's not snow on the ground. What it means is that the snow is actually being obscured by trees in the mountains. And so the visible satellite is picking up the trees, but not the snow beneath it. You go further north, and you begin to pick up more snow as we get more into farmland. If you move further west, you'll see that our clouds, also not surprisingly, are really reflective, high albedo, and they're also white, but you'll notice that the clouds have a more diffuse appearance than the snow cover. I also want to point out, if you take a look at the snow cover, you can see that we have bodies of water cutting through the snow cover. So here's the Susquehanna River, and I think this has actually been helped along a little bit with a little bit of blue added. But here's the Susquehanna River cutting through it. You can see some lakes and streams cutting through north and west of Philadelphia. And again, you can see the topography. Here is the Chesapeake Bay right here that the Susquehanna empties into. The Delaware Bay right here. The Delaware River empties into this. So you can see these bodies of water pretty well. So the rivers and forests are apparent in the snow cover in eastern Pennsylvania. Now, here are some better examples of satellite imagery visible again, and this is black and white imagery now. We can see, here's Iowa, by the way, Minnesota to the north, Nebraska to the south and west, and then Kansas to the south of Nebraska. And you can really see quite well streams and rivers cutting through the snow in Iowa, as well as a lot of lakes dotting through the snow in Kansas, and again, more river cutting through the snow in Nebraska. So you can really tell pretty easily when there's snow on the ground versus cloudiness, just because you can see these geographic features that cut through the snow cover. And again, if we go back to this image of Pennsylvania, it's pretty easy to tell the appearance of clouds versus snow on a visible satellite image. Okay, let's move on to infrared satellite imagery. Now, one of the biggest benefits of visible satellite imagery is that visible satellite imagery has pretty high resolution. And in fact, the resolution of this particular satellite image is not all that great. But you can pick out a lot of detail really, really easily. The problem with visible satellite imagery is that it's only good during the daylight hours. So in better words, the sensor, the visible sensor on a GOES satellite will basically only be able to measure albedo during those hours when the sun is above the horizon and there's visible energy coming into the atmosphere to be reflected back out again. During the nighttime hours, when the sun is below the horizon, there is no visible energy coming in to be reflected by the Earth and the atmosphere. And so this image during the nighttime hours would simply be black. You wouldn't see any clouds, you wouldn't see any snow at all. And so we're really left with a bit of a difficult situation here in which satellites are of no use to us at night unless we figure out some other way to sense the Earth and the atmosphere when the sun is below the horizon. Fortunately for us, this is actually a pretty easy fix because it turns out that all objects, so the Earth, the atmosphere, you, the chair you're sitting in, all objects that have mass and a temperature also emit energy. Now, emit is different than reflect. Objects that reflect energy have to receive that energy to then reflect it back out again. When an object is emitting energy, it is actually giving off energy. It's actually emitting it. It's giving it off. And so the Earth and the atmosphere don't just reflect visible energy, they also emit energy as well to space. Now, the type of energy that the Earth and the atmosphere emit is infrared energy. So if you take Geography 1250 Weather and Climate with me, we cover this in a lot of detail. And based on the Earth's surface and Wien's law, the Earth's surface and the atmosphere emit infrared energy. And so the Earth and the atmosphere actually emit infrared at a number of different wavelengths within the infrared range, but because it is emitting 24/7, we can actually measure during the nighttime hours as well as the daylight hours how much energy infrared the Earth and the atmosphere are emitting. Now, the amount of energy that is emitted depends on the temperature. And not surprisingly, the higher the temperature a surface or an object has, the more infrared energy it's going to emit. So we can use this information about the fact that the amount of infrared that is emitted by an object is temperature dependent to actually assign a temperature to the Earth and the atmosphere on an image. So we actually can create infrared satellite images using an infrared sensor. And so here is an example of a black and white infrared image. Now, I want to be clear here as I'm going through these images. You're probably noticing, obviously, that everything is kind of black and white. And for a lot of you who already look at satellite imagery online, you know that satellite imagery on an internet site is color-coded. There's a lot more color than our textbook is providing. But because our textbook is looking at satellite imagery primarily in black and white for visible and infrared, we're going to do the same thing in this PowerPoint presentation. So what infrared satellite sensors do is they basically measure the amount of infrared energy that is emitted by the highest object at a location. So if there are no clouds, what the sensor is measuring is the amount of infrared energy that is emitted by the Earth's surface. If there are clouds, then what the sensor is doing is it is censoring the amount of energy that is emitted by the cloud top. So there's actually quite a bit of detail on this image in spite of the fact that it is black and white. And although we don't have a legend or a scale at the bottom of this image, it's kind of apparent just by looking at it what's going on. First of all, the Earth's surface relative to clouds is warm. It's relatively warm. And so these warm surfaces are color-coded dark. And the darkest colors refer to the warmest surfaces. And so what you'll notice, in particular, if you look real carefully, you'll see that the Philadelphia metropolitan area, the Baltimore, D.C. metropolitan area, and obviously the New York metropolitan area are all color-coded really, really dark. These are urban heat islands. They're the warmest locations on the map. There are a couple of other dark splotches, but these are the biggest ones, and these basically correspond to very warm surface temperatures over urban areas. You'll see in more rural areas and in mountainous areas that the colors tend to be a little bit lighter, a little bit grayer, so the temperatures are lower. And then you'll notice that the cloud tops are bright white. Not surprisingly, the cloud tops are colder, they emit less energy, and so what we do with our algorithms when we create these maps is we basically color code to basically reflect, and that's probably a bad use of word, to basically illustrate the amount of energy that's being emitted by the surfaces. Warm surfaces that emit a lot of infrared, we color code dark, and as the surfaces become progressively cooler, we shade them through the grays and then eventually the whites. Now if you look real carefully at Lake Erie, at the Chesapeake, the Delaware Bays, and the Atlantic Ocean, and you'll see the Susquehanna River really, really well here. And you'll notice that all of these bodies of water are gray. Now these bodies of water, it turns out, are much cooler than the land surface, and so they emit less energy, less infrared than the land surfaces do, and so we color code these surfaces gray. And in fact, this is an image that was actually taken during the spring when the ocean, the Lake Erie, and the bays are all relatively cold. And so you'll actually see these are actually color-coded gray because they're cold and they're emitting relatively little infrared when you compare them to the land surface. And if you look carefully, for those of you who are New Yorkers, you'll also see the Hudson River winding its way through eastern New York to New York City right here. All right, so this is how infrared works. So again, this is a black and white image, infrared image of Pennsylvania on an early spring day. So just to compare visible and infrared, this is actually going to be a set of 4 images of Hurricane Katrina just before it makes landfall in southern Mississippi in September of 2005. Actually, late August, August 28th of 2005. So here's the hurricane just before it makes landfall. It's a Category 5. You can see it's a monster hurricane, really well-defined eye. This is a visible image, so this is all a measure of albedo. So we're color-coding basically these dark surfaces, basically low albedo, and we're color-coding them dark. And then obviously cloud tops, high albedo, we're color-coding them white. This is infrared from the same time. Now it's color-coded. And if you take a look at the legend, this legend basically gives us the temperature of the surface in degrees Celsius. Now remember, what infrared sensors are doing is they are measuring the amount of infrared energy that is emitted by the highest object at that location. So where the object is basically the Earth's surface, a lot of energy is emitted, and we can actually use Wien's law and stuff on Boltzmann's law to actually figure out what the temperature of that surface is. And so you can see temperature of the surface upwards of 30 degrees Celsius, 86 degrees Fahrenheit. But as you can see, as we get to the core of the hurricane, the eye wall right here, you can see that these cloud top temperatures are actually colder than 70 below 0 Celsius. So incredibly cold cloud top temperatures right around the eye of the hurricane. This is a water vapor image, which we're going to talk about in a few moments. So water vapor imagery is a type of infrared image. It's using a different wavelength of infrared, basically that focuses on preferentially on emission of infrared by water vapor in the atmosphere. And again, we're going to talk about that in a moment. here's our legend right down here. And then here's our vapor image 12 hours later. So as bad as Hurricane Katrina was and the amount of death and destruction that it caused, fortunately, it actually ingested a bit of dry air into its circulation during the 24 hours leading up to landfall. And as a result of that, instead of coming into Louisiana, Mississippi as a Category 5 storm, it came in as a strong Category 3. Had it come in as a Category 5, the destruction and the death toll, no doubt, would have been much, much greater than it was. And obviously, it was an incredibly devastating storm, just as it was as a strong Category 3. Okay, let's talk about vapor imagery just for a few minutes here. So vapor imagery, again, what vapor sensors do is they're again measuring infrared energy that is emitted by the Earth and the atmosphere, but it's at a slightly different wavelength of infrared. And so what it's doing is it's measuring infrared energy that is emitted preferentially by water vapor. So this is an image from the 28th of August, 2018. And there's a lot going on in this image. And so what you'll notice that it's kind of very smooth looking. There's a lot of swirls of grays and lighter grays. And then you'll see, obviously, there are these splotches of bright color on the image as well. Now, when the sensor is actually measuring energy that's being emitted by vapor in the atmosphere, this is where we have our blacks and grays. When you see these much brighter colors, this is typically contamination by very high clouds and water droplets and ice crystals. So we don't really spend a lot of time focusing on these bright colors because what we're really looking at here is contamination from cloud. We focus much more on the grays and blacks. Now, just like infrared imagery, what a vapor sensor on a GOES satellite is doing is it is measuring energy that is being emitted by the top of the vapor layer. So basically, it's sensing where the highest altitude of vapor is at a given location, and it's sensing the amount of energy, infrared, at that wavelength that's being emitted by that vapor, just at the top of the vapor layer. So it has no idea what's going on beneath the top of the vapor layer. The legend at the bottom, again, is temperature. And so what we're doing here is we're basically looking at the temperature at the top of the vapor layer. Now, when you go back a slide or two and you take a look at the infrared images and those legends, what you'll note is that the highest temperatures, the warmest temperatures in a vapor image are a lot lower than they are for infrared. So the reason for this is because there's always some vapor in the atmosphere. And so the top of the vapor layer is elevated above the Earth's surface. And so typically the top of the vapor layer, even in very tropical locations, has a temperature typically not much warmer than about 0 degrees Celsius or 32 degrees Fahrenheit. And then temperatures go down from there as the elevation or the altitude of the top of the vapor layer gets greater or higher. So we always have some vapor in the atmosphere. So what vapor images allow us to do is they allow us to get some idea of the depth of the vapor in the atmosphere and give us an idea of just how much vapor there might be in our column. So again, we focus on the grays, on the swirls, and we really don't focus too much on this contamination that is given to us by the purples, the greens, and the blues, where we have these much lower temperatures. Okay, so again, what a vapor sensor is doing, it's measuring the amount of infrared energy that is being emitted by the top of the vapor layer at a given location, and then we're using Stefan Boltzmann to convert this into a temperature for the top of that vapor layer. And this is from 1138Z on the 28th of August, 2018. So here's an example, and this is from your text. Here's an example, again, unfortunately going back to black and white, which you kind of lose some of the details here. But this is an infrared image. If you look real carefully, here's Florida where my cursor is, moving through Mexico and through Central America into the northern part of South America. And what you'll see is a lot of milky cloudiness over Central America and the Caribbean and the Gulf of Mexico. These milky shades indicate that the cloud tops are low and they're emitting a fairly large amount of infrared energy. And so they're being color-coded this milky gray to indicate that they're low. If you take a look at a vapor image from the same region for the same time, you'll see that it looks quite a bit different. Now, before I actually dive into the details, let's focus on these numbers right here. These numbers are surface dew points for these stations over Central America and Florida. And so what you'll see is the dew points are in the 50s, 60s, and we have a couple of low 70s here as well. So the dew points are relatively high. It's a fairly humid day over these areas, and this is March 8th of 2015, so it's still relatively early in the season. By the time you get into the summer, these dew points will be well into the 70s, and you might even see an 80 or so at a couple of locations. But still, pretty humid, a lot of vapor at the surface, and so you see a lot of low cloudiness here on our infrared image. So why is it gone? Why are these clouds gone on our vapor image? So if you take a look at the vapor imagery, and unfortunately it's black and white, you'll see this bright white here, which is contamination from droplets and crystals in this extensive cloudiness over northern Mexico, going to Texas and the south central US. But where we don't have such extensive high cloudiness, you'll see that we have this lighter shading of milky gray. This is where the top of the vapor layer is relatively high. And then you'll see where we have this black right here, the top of the vapor layer is low. So what we have going on here is a low top of the vapor layer. However, the top of the vapor layer here is still higher than the tops of these clouds that are being sensed by the IR satellite sensor. And so the top of the vapor layer is actually overlaying and obscuring the clouds that we see here on this infrared image. So this is a really nice illustration of basically vapor, the top of the vapor layer being higher than the tops of these clouds, which shouldn't be a surprise. I mean, you need for saturated conditions in order to have a cloud to begin with. And so you would expect that you might have vapor actually overlaying these lower clouds, and this is exactly what's going on. So are there clouds over the Caribbean? Yeah, there's still clouds over the Caribbean, so you just see that the vapor is overlaying it. Now this is an important consideration because you need to remember that if you take a look at a vapor layer or a vapor image and you see no clouds here, that does not mean that the conditions at the surface are going to be clear and that it's going to be a sunny day. So just keep that in mind, that it can still be cloudy, but the top of the vapor layer is higher than the tops of the clouds. So here's a nice little graphic from our text to kind of give you an idea of what you would expect to see on a black and white vapor image. So if you have vapor in the lower part of the troposphere, but you get into the upper part of the troposphere and it's dry, what you'll see is that the top of the vapor layer is relatively low. And so this layer being relatively low means that the temperatures are relatively warm, and it's going to emit a lot of infrared, and it's going to be color-coded dark. Now, if the top of the vapor layer extends further up into the troposphere so that you see that the top of the vapor layer causes the upper troposphere to still be relatively moist, so we have a high top, then what's going to happen is the temperature at the top of the vapor layer is going to be pretty cold, and so the top of the vapor layer is going to emit just a little bit of infrared, and we're going to color code that something gray. All right, so a lighter shade of gray. Here is what we saw in our last image, where we had the top of the vapor layer being higher than the tops of low clouds. So again, it's dark, and you don't see any cloud top at all. Now, if you've got really high clouds, then what you might see is this bright white, where, again, you do get some contamination by droplets and crystals, and we tend not to look at the brightest shading, particularly when we're looking at the color coding. You can see this, the southern color really, really well, and obviously there's going to be a lot of vapor there because there are clouds, but you're still getting contamination from the clouds themselves. So on a black and white, this would be white on the vapor imagery. Just to indicate the shading, here beneath the top of the vapor layer is indicating the relative amount of vapor that's in the air beneath the top of the vapor layer. Just keep in mind that the vapor sensor is not measuring any of this vapor beneath the top of the vapor layer. Just one more example, again, straight from your book. This is Africa right here, basically the southern 80% of Africa, Indian Ocean right here, Madagascar, and this is an infrared image. You can see some bright cloudiness right here. We have our bright whites, and then a lot of low clouds over the Indian Ocean and over a lot of central and southern Africa. If we take a look at a vapor image for the same time, you would expect
probably for the top of the vapor layer to be beneath these lower clouds and maybe intersecting or being with the tops of these higher clouds. And this is exactly what we see, where we had these low clouds, now it's just pure black, indicating that the top of the vapor layer is located higher than the tops of these low clouds. So are there clouds over the Indian Ocean? Yeah, there's still clouds over the Indian Ocean, but the vapor image is not going to give it to you, at least not for the low clouds. And then table 5.1, which I'm not going to go through in any detail here because you can read the text, but it gives you the guidelines for interpreting clouds on visible, infrared, and vapor satellite imagery. So go ahead and have a read of this. And just remember that while we're looking at black and white satellite imagery in our class, obviously you're going to need to take a look at new images that you're looking at on the internet and make sure that you're reading those legends for infrared and vapor imagery so that you actually know what colors correspond to the temperatures that you're seeing. Actually, I should say that what temperatures correspond to the colors that you're seeing. Okay, that's all I'm going to say about satellite imagery here. I'm going to move on to Doppler radar. So this first image is from the National Weather Service. Actually, it's a little bit antiquated now, but I like it. And this is basically an image that shows you the National Weather Service Doppler radar network. And what you'll note is that, in fact, there actually aren't a huge number of Doppler radars across the continental United States, roughly 100 of them or so. Some states have 2, a lot of states actually have 2, and then obviously our big states, Texas, California, have way more than 2, and you'll see that New York has a couple more, Florida has a couple more, but if you add it all up, basically roughly 100, a little bit more than 100 Doppler radars across the United States. So don't get confused with looking at the local news and Bigfoot Doppler 95,000 or whatever. These are basically the big Doppler radars that the National Weather Service uses that you're going to see online with National Weather Service websites. So here is a very early radar image of a hurricane over the Pacific Ocean that was taken by a U.S. warship. And if you take a look real carefully, you'll see these little radials of white, bright light that are coming out from this image. So it turns out that this, so basically what you're seeing here is that this image was basically from a ship that was in the middle of this hurricane. Probably not a good place to be. But this is a reflectivity image. Here's the high of the storm right here. And so this is a very, very early image. Now, when I'm teaching this class in the classroom, I tend to like to talk a little bit about the history of weather radar. So Doppler radar was not around in 1944 during World War II. So this is radar that was basically purposed from sonar, basically used to measure objects, and radar was basically used to measure objects in clouds, so droplets in ice crystal that were then scattered back by the clouds to give us an idea of where clouds and precipitation were located. And obviously, this is very rough, but the military used this as an idea to get an idea of their military operations during the Second World War, in this case, in the Pacific. So let's take a look at something a lot more contemporary. And this is a base reflectivity radar image from 1938Z on the 29th of August, 2022. By the way, since this is our first PowerPoint, our first chapter, I just want to remind you that Z corresponds to Greenwich Mean Time. So this is Greenwich Mean Time, so this would be 7:38 p.m. Greenwich Mean Time. For us here in Bowling Green, we would be subtracting 4 hours to get to Eastern Daylight Time. So instead of this being 1938Z, this would be 15:38 Eastern Daylight Time in the afternoon, so 3:38 p.m. Eastern Daylight Time on the 29th of August, 2022. Now the way that base reflectivity works is the Doppler radar, what it does is it's sending out pulses of microwave energy, and I want you to remember that it's microwave. It's sending out pulses of microwave energy, and what's happening to this microwave energy is one of a few things. If there are no clouds in the sky, the microwave energy pretty much goes straight out to space, and that's the end of the story. Nothing is scattered back to the radar, and so this is actually basically showing us clear. Now, if there are clouds, but these clouds are not producing precipitation, what will happen to that microwave energy is that the droplets and the crystals in the clouds will scatter some of that energy back to the radar. But the signal, the scattered signal, will be relatively faint, and we know that that faint signal means that the clouds are not producing any precipitation. And again, you'll see no colors on our map. Now, if the clouds and the precipitation are scattering a lot of energy back to the radar, in other words, the scattered signal becomes increasingly intense, more energy is being scattered back, at some point we will know that that scattered energy is corresponding to clouds that are producing precipitation, and we'll begin to color code these clouds. And so if you take a look at the legend on the bottom of the screen, what you'll see is we begin to color code at, and the unit we're looking at here is decibels, we begin to color code at about 5 to 10 decibels for our faintest signals where we have clouds that might be producing precipitation. And so as the signal gets stronger, we go through the greens to the yellows, oranges, and reds. And so these stronger signals correspond to higher rainfall or precipitation rates. So the larger the signal, the higher the dBz, the more precipitation that's being produced by these clouds. And so what Doppler radar in base reflectivity mode is doing is it is measuring the intensity of the scattered signal from the clouds back to the radar. Now, before I move on, I just want to make sure, and I do this in weather and climate, so a lot of you know this, but just to be complete here, I want to make sure that you understand the difference between reflection and scattering. So when an object reflects a signal, what the object is doing is it's taking the energy that it's encountering and it's sending all of that energy, all of it, back to the source. So if clouds reflected energy, they would take the entire microwave signal and they would reflect all of it back to the radar. Instead, what's happening here is that the droplets and the crystals in the clouds, they are scattering the energy. So the droplets and the crystals are interacting with this microwave energy. And what's happening is when the energy is being scattered, what the droplets and crystals are doing is they're basically sending the energy out in all directions, not just back to the radar. So only a part of the original energy is being scattered back to the radar by the droplets and the crystals that comprise the cloud and the precipitation. So calling it reflectivity is an unfortunate use of wordage here. It's an unfortunate word. So base scattering would be better because in fact the clouds and the precipitation are not reflecting, they are scattering the energy. Just understand that when you're looking at a base reflectivity Doppler radar image, what you're looking at here is a measure of the microwave energy that's being scattered back to the radar by the clouds and precipitation. All right, I would ask if there are any questions, but since I'm recording this in my home office, I know there aren't. So I'll just keep going on. All right, so what base reflectivity does is it is basically an image that is put together as a result of Doppler radar sending out its microwave pulses at an angle of 0.5 degrees from horizontal. All right, so what we're taking a look at here is basically a base reflectivity image. And if you take a look, you'll see this KIWX here. The Doppler radar is the KIWX Doppler radar. It's located in North Webster, Indiana. So this is for a signal that, or I should say an image, that's basically being put together as a result of a single Doppler radar basically sending out its signal at a ½ degree above horizontal in a circle around the Doppler radar. So North Webster, if you take a look real carefully, you'll see this little dot right here to the northwest of Fort Wayne. That's where North Webster is located. So this is the base reflectivity image for this particular time. Now, we can take a look at composite reflectivity for the same exact time, and you'll see that the image looks a little bit more detailed, a little bit more intense when we're taking a look at composite reflectivity. Excuse me for my coughing. I'm actually recording this video, and it's the first talking that I'm doing for a lecture since the end of spring semester, and we're in the middle of June as I'm recording this, so my voice isn't used to talking so much, so it's a little bit dry, and I'm going to do a little bit of coughing. As I make more of these videos, I will not cough as much. So anyway, composite reflectivity, what's happening in this case is that the Doppler radar is basically varying its beam elevation between 0.5
and 19.5 degrees above horizontal as the radar is going around in a circle above that pedestal where the Doppler radar is housed. And so what happens when we take a look at composite reflectivity is that instead of just taking a look at a single slice, as we do with base reflectivity, what composite reflectivity allows us to do is to get a sense of where the most intense precipitation is located in our cloud through a good depth of that cloud. And so what composite reflectivity does is it just basically plots reflectivity for the highest reflectivity in that vertical slice at a given location. And so you'll see, if you just take a look at any given location, particularly where on base reflectivity we have some pretty bright returns, so we have really high reflectivities, where you'll see on composite reflectivity is that it's even brighter. In better words, the strongest reflectivity is actually happening at an altitude above 0.5 degrees. All right, so this allows us to get a better idea of where the strongest returns are located. And what we see in this particular image is that with composite reflectivity, the largest reflectivities, in better words, the largest droplets are located, and maybe hail, where you see these little bits of white right here. This is probably hail. So the hail is actually located above where the single slice gave us our base reflectivity information. So to give you an idea, and again, this is from our text, this is an example from the 23rd of July of 2010, and this is for a thunderstorm that produced the Vivian, South Dakota hailstone, which is the largest hailstone on record. It is a hailstone, and you can get online to get pictures of this. You can just do a search, but the diameter of this hailstone was around 8 inches, and it weighed almost 2 pounds. You would not have wanted to be where this hailstone fell, or you would not be here to talk about it. All right, so this is a huge chunk of ice that fell out of the sky. And so here's basic reflectivity. Here is the altitude in terms of angle of 0.5 degrees. You can see that the reflectivity is really high. It's about 65, 70 decibels. Here is 0.9 degrees. So you can still see we're picking up a lot of our highest reflectivities right here. Here's 1.5 degrees, still picking up our highest reflectivities. So in better words, really large hail at these low elevations. But by the time you get to 1.8 degrees, what you see is you lose the highest reflectivities. So our largest hailstones, our biggest reflectivities, our largest scattering is actually located between about 0.5 and 1.5 degrees above horizontal. Now, one thing that we see a lot of during the wintertime when we're looking at reflectivity images is that we tend to get a lot of overshoot of low top clouds. So when we're getting snow, snow tends to be produced by stratiform clouds, and thus we're taking a look at lake effect snow, which is more convective. But when we're getting snow, just steady snow, it tends to be produced by stratiform clouds. They have relatively low cloud tops. And if the cloud tops are relatively low and the Doppler radar is fairly far away, when we have Doppler radar, what will happen is the beam will overshoot these low cloud tops and we won't pick up precipitation at all. And in fact, here in Northwest Ohio, this is a big problem because the 3 closest Doppler radars, which are in North Webster and Detroit and Cleveland, and you can put in Wilmington there as well for Central Ohio, all of these Doppler radars are relatively far away from us here in Northwest Ohio. So when it comes to low clouds that are producing precipitation, we're in a little bit of a radar hole. And particularly during the wintertime, what you'll see is that you'll see snow or precipitation surrounding us on Doppler radar from these sites, and you'll see very, very little going on over us here in Northwest Ohio, in spite of the fact that it's actually snowing outside. And the reason for that is that the cloud tops are low, and these Doppler radars, their beams, even in base reflectivity at 0.5 degrees above horizontal, are actually overshooting our cloud tops. Now, in addition to actually looking at reflectivities and getting an idea of precipitation intensity for just a slice in time, we actually have algorithms where we can just basically look at a continuous loop of Doppler radar and take a look at our rainfall rates based on reflectivities, and we can actually calculate accumulated precipitation for a region, or for any given location for that matter. So here's an example, and these examples in our text are a bit old, and I apologize for that, but here is an example for the north central part of the country,
And this is a single-day observation from the 5th of June of 2008. And this is from 12Z to 12Z. So this would be from 7 in the morning to 7 in the morning Central Time. And so you can see really well that we have these localized stripes of very, very heavy precipitation where we have amounts in excess of 6 to 8 inches, particularly over southern Nebraska and extending into southwest Iowa, and then some more in Indiana and going into southern Ohio. So this is really, really helpful. It's not as precise as measuring with an instrument, but it does give us the opportunity to get a large-scale spatial mosaic of what rainfall rates probably were without us having to measure every single one of these points. Here is a 30-day total, and this was created on June 16th of 2008. So basically this goes from mid-May to mid-June, and this was during a period of excessive rainfall in the middle of the country. And so you can see, particularly over Iowa, you can see a large expanse of real estate where there are 10 to 15 inches of rain, a couple of localized areas in Nebraska, Kansas, Iowa, and Indiana where amounts exceeded 15 inches, and two really localized areas in south central Indiana where Doppler radar estimates were greater than 20 inches. So this is a really dramatic example. Now remember, 20 inches, you're talking just a little bit less than an inch per day averaged over a whole month. So it's just an immense amount of rainfall, while here in northwest Ohio, things were a lot closer to average, 3 to 4 inches during this period of time. Here is a base reflectivity image with a hook echo over Parkersburg, Iowa. Hook echoes are, and we'll talk a lot more about this as we get to the end of our class, hook echoes actually on base reflectivity indicate that we have a mesocyclone in a supercell thunderstorm, and we have counterclockwise rotation, and this little hook of precipitation on the western side of our mesocyclone. And we typically see with a hook echo, this little hook of reflectivities, that at the tip of the hook, this is where we typically find tornadoes in supercell thunderstorms. And so knowing this signature on base reflectivity is really important. And so we will see this on base reflectivity images when we're looking at tornadic situations. And again, we'll say a lot more about this, some in this presentation moving forward, but a lot more when we get to chapters 14 and 15. All right, now, I want to talk more about Doppler radar in velocity mode. This is actually where we look at the Doppler effect as it pertains to our radar. So imagine that you've got, and this is a schematic, I actually stole this from a different website. So this is a schematic of the National Weather Service Doppler radar sending out its pulses of microwave energy. And this area of cloudiness with rotation here is meant to indicate that we have a supercell thunderstorm with a counterclockwise rotating mesocyclone. Now, if the radar were in reflectivity mode, what the radar would do is it would send out these pulses of microwave energy, and then what the cloud would do, is the droplets and ice crystals would simply scatter microwave energy back to the radar, and then the radar would use this information to put together our base reflectivity image. Now, when we take a look at radar in velocity mode, what velocity mode does is it uses a Doppler effect to give us some sense of whether the motion in our supercell is moving toward the radar or away from the radar. So imagine now that you're looking at this supercell from above with our radar, basically this circle with the X. And what this arrow, this curved arrow is meant to do is basically to indicate the movement of the radar in a circle around its location. So the radar is moving around in a circle on its pedestal, and it's sending out these beams of microwave energy in all directions. So we're just going to focus on these positions 1, 2, 3, 4, and 5. And so what the Doppler radar is doing now, it's sending out these pulses of microwave energy. And what you see from mesocyclone is these arrows indicate the motion at these points along the mesocyclone, along paths 1, 2, 3, 4, and 5 of microwave energy being sent out by the radar. So what you'll notice is that at beam positions 1 and 2, the motion of this mesocyclone is toward the radar. In better words, the motion is toward the radar as we have this counterclockwise rotation. At positions 4 and 5, what you'll notice is
the motion is away from the radar. Now, it may not be directly away from the radar. In better words, at position 4, we basically have motion that is somewhat away from the radar versus position 5, where it's completely away from the radar. And similarly, at position 2, you'll see that there is motion that is angled toward the radar, whereas position 1, the motion is directly toward the radar. So what Doppler radar does when it's in velocity mode is it basically uses the Doppler effect to determine whether the motion is toward or away from the radar. Now, pure classic Doppler motion doesn't use microwave, it uses sound waves. And so you can tell when an object like a train is moving towards you or away from you, because what happens is as the object is moving towards you, the sound waves are compressed and the pitch of the sound goes up. If the motion is away from you, then what happens is that the sound wave is stretched out and the pitch of the motion goes down as the frequency of the wave gets lower as the wavelength gets longer. All right, so what we're looking at now is as the motion is toward the radar, instead of sound waves being compressed, what we now know is that the microwaves are compressed when the motion is toward the radar. When the motion is away from the radar, what happens is that the microwaves are stretched out a little bit, and so the wavelength is lengthened and the frequency goes down. And so what we look with when Doppler is in velocity mode, what it's measuring is whether or not the frequency is going up. In better words, the wavelength is being compressed and the frequency goes up, motion toward the radar, or motion away from the radar, the wavelength lengthens and the frequency goes down, and again, motion away. So here is our Doppler effect. In better words, when we have Doppler motions away from the radar, we have this stretching out versus this compression when it's toward the radar. All right, so again, take a look at it. Top figure, motion toward the radar, compression of the wave, higher frequency, and we know motion is toward the radar. With motion away from the radar, the beam gets stretched out a little bit, lower frequency of the scattered signal, and we know that the motion is away from the radar. Now, here is an example. I'm going to do these side by side. Here's an example of base reflectivity. This is of a supercell thunderstorm that produced a tornado. Here's the hook echo, and here's Oklahoma City and the Oklahoma City Doppler radar. Here is the velocity image. And if you look really carefully inside the circle, you'll see this color shift. So we have some green and we have some red. The green is actually toward the radar and the red is away from the radar. So we have toward and away. So basically what we see is our rotation because we have this shift in motion toward and away. And so we actually can see the rotation here. Now it's not as exciting looking on velocity as it is on reflectivity, but we see this shift, this phase shift in the frequency over a very small distance, and that allows us to figure out that we have rotation. Now the radar itself is located right here. And so here's our motion toward, green, away, red, and then you can see this general motion, and then within this general motion, you see this phase shift over a very small area that indicates that there's rotation in this area right here. Now, I'm not going to spend much time with this legend because it's not a very clear legend to read, but these colors correspond to motion in knots. The negative numbers, which are our greens right here, negative numbers always indicate motion toward the radar, right here, and the red indicates motion away from the radar, right here. So positive, red, motion away, green, negative, motion toward. Here's the radar, here's our green, toward radar. Here's our red, away from the radar. Again, here's the radar sight. When you put the motion away and the motion toward together, you'll see that we have counterclockwise rotation right here. So within this broader area of motion toward and away from the radar, you've got this area of rotation within the black circle. And so velocity imagery allows us to identify rotation. Now, the hook echo is an illustration of that rotation, but reflectivity is still just reflectivity. It's still just measuring scattered signal back to the radar by droplets and crystals. To actually measure the rotation, you have to look at the velocity image, and you see it right here.
So here are some simple examples. Here is an example from the Milwaukee Doppler radar site. This is a base velocity image from 2143Z on the 28th of August 2022. Here's the Milwaukee radar site right here where my cursor is. You can see this little dot. You can see the greens and the reds. If you take a look at the legend at the bottom, you'll see that the greens are negative numbers, again in knots. This is motion toward the radar. The red, positive numbers, again in knots. This is motion away from the radar. So what you can see here is that there is a general south to north motion. South to north motion. So again, negative, green, toward the radar, red, positive, away from the radar. And you'll notice the gray right in between here. This is where we have zero Doppler velocity. In better words, where we have motion toward the radar and then suddenly away from the radar, where we have this gray right here, what we see is that the motion is neither toward nor away from the radar. So the radar is sending out a pulse of microwave energy here and here. The motion is south to north, and so the motion is perpendicular to the microwave beam, and so there's no phase shift. Right here and right here, there's no motion toward nor away from the radar. We won't talk about the grays very much. We'll just focus on the greens and the reds so we can get a general sense of the motion. So again, green, these are negative numbers on our legend, velocity toward the radar. Red, positive numbers on our legend, this is away from the radar. The shade changes as the distance from the radar increases. So I want you to note that as you move away from the radar, the reds get brighter, the greens get brighter. The reason for this is that as you move further away from the radar, what's happening is the radar is sensing higher up in the troposphere. As you go higher up in the troposphere, the wind speeds are going to increase. And so you're seeing this brighter red and this brighter green as you move further away from the radar, indicating faster motion. So again, that's just because the radar is sensing higher up in the troposphere. Now, the last thing I want to talk about very quickly is wind profiler. This is, again, a remote active sensor. Here's a picture of a wind profiler. Now, what a wind profiler does is it provides us with a sense of how wind direction and speed are changing just at this location as we go up through the atmosphere. So the profiler is located at the Earth's surface, and what it's doing is it's sending energy up through the atmosphere at this point, and then it is sensing the energy that is sent back to it by the atmosphere to get an idea of the wind direction and speed. So it is an active remote sensor. And so here is a measurement by a wind profiler at Norman, Oklahoma from the 20th of May, or I should say from the 13th of May, 2013. Oh my goodness, I'm getting these dates wrong here at the end. From the 20th of May of 2013. So what you have to do here, you have to take a look at the bottom first. These are the times in Greenwich Mean Time. All right, so these are the times, Greenwich Mean Time in Z 1921 through 2003. And then above, on the y-axis, what you're seeing are altitudes in kilometers. So this is Norman, Oklahoma, going up through the atmosphere at the location of the profiler for each one of these times. And so this is basically a profiler sensing every 4 minutes what's going on over Norman, Oklahoma. And you'll notice a couple of things here. Not surprisingly, as you move up from the Earth's surface, the wind speed is increasing. So you'll see faster wind speeds. You'll also notice that the winds change direction as you go up as well. So the wind direction at the surface is pretty much just a little bit east of south. And what you'll see is it begins to veer from east of south to southwest. And then you'll notice these wind speed changes as well. And you'll notice that the winds at the surface, the wind speeds vary from about 10 to 15 knots. This is less than an hour that's elapsing here from 1921 to 2000 or 2003 Z. And then you'll see that the wind speeds increase from 15 to 20 knots all the way up to in excess of 50 knots. And you'll see anything greater than 50 knots is color-coded in red, or most of them are color-coded in red. We have some lighter wind speeds color-coded in red as well. When we talk about wind shear, and the importance of wind shear, which is the change in wind speed and direction as we go up through the atmosphere, pretty much through the lowest 6 kilometers, we'll really focus on wind shear that's greater than 35 knots. So in better words, if you go from 20 knots to 55 knots or more in the 6 kilometer layer, that is really strong wind shear, and that's where we begin to take a look for storms that can actually cause rotation. Now, this 20th of May event was again a supercell. We already took a look at the hook echo for it that produced tornadic activity in the Oklahoma City region. So this is basically an example of profilers showing that we had really strong wind shear capable of producing rotation over central Oklahoma during this time, during this 1 hour period in 2013. Okay, that is it. That's all for this first PowerPoint presentation. I know that because I'm producing this and I'm not actually doing anything to sort of clean things up after I do it, I'm just posting it live. It may not be the smoothest presentation in the world, but it gets the signal across to you. And so for those of you who are taking the distance course, here is your Chapter 5 lab assignment. So here are the questions that you need to complete. As you'll see when you go through the introductory video for our class, all of these questions are being put into multiple choice format. So these are all multiple choice questions that you're going to have to figure out. I will give you choices and you'll have to figure out what is correct. And you'll have both the introductory week, our preview week, and week 1 of our course to complete this and submit it for a grade on Canvas. During the introduction and during the preview and week 1 of our class, you'll be able to take the quiz on Canvas for this lab assignment as many times as you like. I strongly encourage you to do this so that you become comfortable with the Canvas quiz tool. You'll only be able to take these quizzes multiple times during the preview and week 1 of our class. Once we move on to week 2 and we start moving more quickly, you'll only be allowed to take each quiz only once. So make sure you take advantage of this opportunity. Take each quiz, take the quiz for Chapter 5 as many times as you can. Canvas will only record your highest score. You'll get the key for the quiz each time after you take it. And so after week 1 of our class, you really should have a perfect grade in our class. Okay, that is it. That's all. I'm going to end this PowerPoint presentation, and I'm going to post it on YouTube. And then when our class begins, when our preview week begins, I will send you the link for the video so that you can view it and then get ready to succeed in our class. So that's it. I'm going to end it all now and post it on YouTube.